Okay, guys, any questions about lab today or any material thus far?
I have a question about one of the problems in our workbook.
Uh-huh.
It was about why one of the compounds that would have done SN1 fastest.
Aromatic?
Yeah. Well, these two aren't aromatic, but why this one's faster
Well,
than that one?
they're not aromatic right there. What's the intermediate in an SN1?
A carbocation.
That's the rate determining step, forming the carbocation.
Right.
Look at the carbocations.
So this one just is heftier to do it because of that. The shape of it? Is it the shape of that ring and that?
Well, it's more than the shape, it's 4n plus 2.
Okay. So even though they're not aromatic, we're still looking at that.
Well, can they become aromatic? Aromatic ions. A carbocation is an ion, cation, ion.
Uh-huh.
But also the handout. Green handout, top of the last page.
I see.
Which one of these reactions will be fastest?
Right.
Okay? It's the same question.
Right, but I wasn't sure why, when I was looking at that one even, it says that, but, okay.
Well, hopefully
But
we
this we're
showed
going
that
from
because
hydrogen,
when this ionizes, it's going to make carbocation here, right?
right,
That carbocation will be aromatic,
okay,
and that's easy to form.
okay,
This carbocation over here will not be aromatic. It will actually be anti-aromatic.
okay,
Very difficult to form.
okay.
Okay, Friedel-Crafts. Friedel-Crafts. Number of issues or problems with Friedel-Crafts. Alkylation. Okay, we're first doing alkylation, just putting an alkyl group on. Plain carbon group. Carbocation chemistry. Polyalkylation. You try to make just isopropyl benzene. Instead, you end up with diisopropyl, triisopropyl, etc. And many products. Hard to purify. Let's now look at Friedel-Crafts acylation. Acylation. Acyl group is a name for a ketone group. Okay? Could theoretically be an H here, but usually it's a ketone from an acyl group. We can get this by reacting an aromatic here with an acid chloride, or called an acyl chloride. Acyl, carbonyl in R group, chloride. It's often called acid chloride because they come from carboxylic acids. This was on the functional group list in Organic 1. Yeah? Okay. Aluminum trichloride. Mechanism very similar. Let's look at it. First step is the chlorine here will add to the Lewis acid. And that will give Al minus. Make the chlorine positive. Now this chlorine will leave this carbon. I'll come this way so I can end up closer to my reactive ring here. And that will give that carbocation plus aluminum trichloride, right? this may look a little funny. It's what was originally an sp2 carbon, carbocation. Usually that's bad. But this is actually okay, and we've actually seen this before. We can do resonance of this. If we come down here and move those electrons down, we get what? Carbon. How many bonds to oxygen now?
One. Oh.
Someone say one?
I was moving the wrong electrons.
Well, there's two there, and then we make another. That should be three, right? And how many lone pairs on oxygen? One. Where's the charge at now? Here. And we have a resonance stabilized species. I would say carbocation, but the charge is actually on oxygen. But what is this? Where have we seen this before at? It's like a carbonyl positive resonance structure. We saw this from organic 1 where? Mass spec. What's that called? Acyl. Yeah. Acylium ion. We saw this in mass spec because ketones, aldehydes, things can cleave to make a resonance stabilized cation. This is the major resonance structure, more bonds. Acylium ion from mass spec. We can make acylium ions by complexing acid chlorides with the Lewis acid, and then when that chlorine ionizes, we get the acylium ion. Well, the ring will react with the acylium ion in an EAS mechanism. We can react with any resonance structure. Any position on the ring here is the same. My pi bonds aren't drawn in too precisely. Maybe I need to redraw my benzene ring. How about these electrons? Okay, the pi bond can be either line here. It can be on the inside or outside. It doesn't matter. These electrons come down here, attack carbon, and these move here. Or you can attack this carbon right here and you don't have to move anything. You can always work with any resonance structure. Neither one is real, right? The true structure is in between. I'm not working with the true structure in between. I'm working with either one of the fake structures you can work with. If you work with this one, you add here, because it says have dipole, okay, but we attack the carbon, and this gives new bond to carbonyl, right? And R group, there's an H here, carbocation there. And then something takes the H to restore aromaticity. Well, we've done this before. One of these bonds from the aluminum can break away and go make bond to H. And these electrons can move here. And that would give that plus aluminum trichloride reform. So it's the same LDAS mechanism, it's just we have a new electrophile. And the electrophile here is the acylium ion, yeah? Everybody remember seeing acylium ions with mass spec? Did you guys cover mass spec in organic 1? Acylium ions? Yeah? Is that right? Is that familiar? Anybody? Did you cover acylium ions in organic form?
It's been a while.
Okay, final exam was comprehensive. Okay. Now, acylation doesn't have as many problems as alkylation. For example, you're never going to get polyacylation. Let's say we do this with this acid chloride, and we make this ketone here, this aryl ketone. Will that acylate again? Why not?
Because you now have a strong deactivator on your benzene ring.
Right, we added in this case a deactivator. It's a carbonyl, it's a group 4. And what do we say about rings with group 4 substituents, metadirectors? They don't do Friedel-Crafts reactions. So it will not acylate again. And so you don't have the problem of polyacylation. You also don't have the problem of carbocation rearrangements because the acylium ion will not rearrange. It's resonance stabilized. And we may show that. Now, remember compound A on the previous page or two? Where when we tried to make it, we actually, what was the yield of compound A if we did an alkylation, Friedel-Crafts alkylation?
With just the chlorine on the,
35%.
Okay, 35%. But instead we got a rearranged product with a yield of what, 60 something?
60 cents.
Okay? A better way to make compound A is shown here. And they do reaction. That is, these aryl ketones, the oxygen can be removed to make the plain alkyl group, which would be compound A from the previous page. And you keep the same number of carbons, 1, 2, 3, 4. 1, 2, 3, 4. We just remove the oxygen from the, what do you call the carbon next to the benzene ring? Benzylic, yes. We remove the benzylic carbonyl oxygen. Okay? This can be done 3 different ways. Hydrogen gas with a transition, with a precious metal catalyst will do it. Okay? We're not going to look at the mechanism for that. But it will do it. By the way, that is a reduction, right? We're removing oxygen. How many bonds to a more electronegative did this carbon have? 2. How many bonds to a more electronegative now? None. It's reduction. We're also removing oxygen. You see it's reduction. Hydrogen is typically reduction. We're also adding H's. How many H's on that benzylic carbon there? None. How many there now? All roads lead to reduction. And hydrogen typically is reducing its terminology. That's where the 2 H's come from. Again, we're not going to look at the mechanism. It's a little convoluted. It's not your traditional, okay. Because it involves a cleavage of the carbon-oxygen bond. That will do it. A more traditional way to do it is a dissolving metal reduction using zinc. Have you ever used zinc before? For reduction? Okay. Zinc, but in this case it needs to be mixed with mercury. Okay? It's sort of an activation with an acid, HCl. Okay? This will remove the oxygen. That's called the Clemmensen reduction. Very classical. Okay? Should be in your textbook. A third way to remove this oxygen is called the Wolff-Kishner reduction. This uses hydrazine and hydroxide. We're not going to look at the mechanism for the first two. They're sort of redox, well, kind of redox. This is redox. That's not really redox, but it's kind of convoluted. We're not going to look at this mechanism now, but we will look at this mechanism during test 4 material. Because during test 4, we'll look at the chemistry of aldehydes and ketones. And this is a ketone. But we're just not looking at aldehyde ketone chemistry right now. So for right now, it's just 3 different ways to do this transformation, and we will look at this mechanism later in the course.
Is there a certain one of those that would give a higher yield than others?
I don't know this reaction. I've never done this reaction. The only thing I can say is the Clemmensen reduction is sort of the most commonly seen. It's the most traditional. And the Wolff-Kishner. The Wolff-Kishner is also very traditional. The one that's not traditional is using hydrogen. You're probably not going to see that anywhere. But I suspect that this might give the best yield. Hydrogenations tend to be pretty good yielding. This one, you're going to have to get rid of zinc when you're done. Anybody ever tried to get rid of zinc when you're done? Zinc salts can be a little tedious, hard to filter. Have any experience with that? Huh? Okay. See, these transition metal salts can be hard to, they're not soluble. You got to filter them. They don't filter well. Okay. The Wolff-Kishner has historically required high temperature. I'm not showing that here. So sometimes your substrate can be sensitive. In the end, it's three methods to accomplish this. And this route, a 2-step route, is better to make compound A. Previous page, we showed a single direct alkylation is not as good. Okay? This is better than direct alkylation. 2-step. Acylation followed by what? Reduction. Say it with me. Acylation followed by reduction. One more time. Acylation followed by reduction. Okay, that's the 2-step route to making, what do we ultimately have here? Alkyl group on the benzene ring. Acyl group on the benzene ring. If you want that to be your final product, you just stop there. You want an alkyl group, you put the acyl on and then reduce it. Much better. Okay? By the way, sometimes you guys try to make an aldehyde using this acid chloride with just an H over here. Okay? And when that ionizes, you make the acylium and then the ring attack. Okay? And sometimes you guys try to do that once we start doing synthesis. This is not a stable acid chloride. Okay? It's not stable. Alright? It's not stable. But you can actually make that in situ by reacting carbon monoxide and HCl. Okay? So these form this in situ, in the reaction. And then, if you got your Lewis acid there, well, then you do your mechanism. This complexes and ionizes. You make the acylium ion. The ring attacks the acylium ion. Okay? And you can get this product. I'm just showing you that. Instead of using that, these two can be used, and that reaction actually works. And if you show the Lewis structures of these two, you can see how they react to give that. Okay? Okay, predict products. Everybody have the first one? Anybody got it? So you got two aromatic rings. Which one is reacting in an EAS mechanism with something? What type of reaction are you doing here?
Isolation.
Okay, which ring is being acylated?
The one with the fluorine.
Okay. Yes? What type of director is the fluorine?
Orthopara.
Orthopara director, yes. How about I just say phenyl here? Yeah? Plus ortho? Just because I put the acid chloride here and not here, doesn't matter. I mean, you can put the fluorobenzene here and the acid chloride here. It's all in the same flask. You got to recognize what's reacting with what. I suspect the main thing that sort of you had to look at twice was two rings. It's just the R group. The R group is a benzene ring. You're not going to do a Friedel-Crafts with this compound, are you? What type of group is this?
Meta director?
That's a group 4 meta director. Can you do Friedel-Crafts with this? No, this ring is not going to react in a Friedel-Crafts. This is not the ring that's reacting. This is just the R group. This ring reacts with the acylium ion that's formed here. It's an ortho-pair director. I showed the pair product. I just chose to show the ortho like that. Everybody good? How about a product down here? Take this single molecule, react it with aluminum trichloride. Catalyst will be here. You'll make the acetylene ion. Right? What can attack the acetylene ion?
The ring.
Ring.
Attached to.
What position? What type of director is this carbon on this ring? That's the atom they bonded. Ortho-pair, it's an sp3 plain carbon. Yeah. Which side do you think is going to react with the acetylene ion that's formed over here? The ortho carbon or the para?
Ortho.
Yeah. The para can't react. At least not. I mean, you may see some very strange things out there where this carbon can react. If this was long enough to be back over here, maybe. But, okay, what size ring we're making over here on the right? What size ring? Hmm?
5 carbon.
A 5-carbon ring? Yes? Get that product right there. And which bond did we just make? I'll highlight the bond we just made, yeah. The orthocarbon bonding to the acetylene ion. EAS mechanism. An intramolecular reaction, yeah? There's 2 below. I'll let you do those on your own unless someone has already done them and would like me to look at them.
I got one of
You've
them.
already got something?
One of them, yeah, that first one. Director here, and then you can carbocation in here after you protonate that.
Protonate, ionize, make what type of carbocation?
Tertiary.
Uh-huh. Yeah. And then do EAS.
Mm-hmm.
Uh-huh. We can look at those a little bit later. Let's see some applications here. This is a synthesis of Tazorac, a medication used to treat acne, I believe. Good looking molecule, yeah? What do we got here? An ethyl ester? What type of ring? Name for this ring? Pyridine ring? What we got here? Alkyne. Benzene ring fused to this non-aromatic sulfur heterocycle. That ring is aromatic, that one's clearly not, correct? Okay, yeah, so we can discuss the architecture of our compound. All right. This shows a multi-step synthesis. Some of these reactions we should be familiar with, and we'll see. Others are going to be more advanced that we will never see. But look at the very first one. Actually, before we look at the first one, let's look at the second one. 16 to 17. What's going on here? The main thing for us is this, which is H+, phosphoric acid, H+. Yeah? Making this bond here, an intramolecular. We got an alkene here. Will it react with H+? Very first reaction we did in organic 1, other than acid base, was reacting an alkene with H+. Where are we going to make cation, on left or right? Right, would be tertiary. Okay. And so these electrons, actually I'm going to draw my H+ down here because they break away from the right, correct? And we get sulfur, boom, boom, boom. Yeah? Let me draw in the new H here. And then what's here? Carbocation. And then what attacks the carbocation?
The benzene ring.
The benzene ring. What type of director is the sulfur
It's a metal director.
that's bonded to the benzene ring?
Metal.
No, this is a atom with a lone pair. It's not a halogen, so it's group 1, orthopara. What is group 1? Atoms with a lone pair but not halogen? Atom with a lone pair but not halogen? Okay. Orthopara director. So the ortho position and so you can do your EAS mechanism, right? I'll just do the first, bam, that attacks. I mean, you can do your same old EAS mechanism. That's how we make that bond I highlighted. Okay? So that's an intramolecular, it's actually an alkylation. Because it's not an acyl group, it's just an alkyl group added to the benzene group. But because it's internal, you're not going to get polyalkylation. Phosphoric acid. P2O5 is sort of an anhydride of phosphoric acid, somewhat. This is aqueous. This sort of gets rid of some of the water. Apparently they need it to be more acidic, probably. I don't know why, but there's fine conditions in every reaction. I wouldn't worry about that for us. What solvent are they using? This is the solvent. What is that? Phenyl with an H. What is that? Do I? Well, phenyl is benzene ring, right? What would this be? That would be phenyl, be that. What would phenyl with an H be? It's just benzene, yes. Because you're not just going to say that for benzene, because this is a substituent. You've got to have something here. You can have a chlorine, you do this, or this. What is that? Yeah, phenyl OH. But what if it's just benzene? You could just say that, right? Just make that an H. Well, that's the common way to show benzene. They're using benzene as a solvent. Now, this is pretty old. Today, they probably replace benzene with some other solvent. Benzene is no longer used in industry. Maybe toluene. Problem is, toluene is more reactive, and toluene might start acylating. Actually, I tell you a good solvent for Friedel-Crafts reactions is nitrobenzene. Sometimes you see nitrobenzene, which is a liquid, used as a solvent for Friedel-Crafts. Why? Because it won't react with in Friedel-Crafts, right? Will nitrobenzene do a Friedel-Crafts? No. It's actually a common solvent for Friedel-Crafts reactions. Okay? Now, benzene could react with this carbocation, but that benzene ring is closer. Okay? Any event, just a little mention of some solvent there. They're actually using benzene. How did they make 16? 16, they started with just the thiophenol. And with base, this became anion, yeah? And then they reacted here, and this came in here, and bam, kicked off the bromine. What type of mechanism is that? That's a good old what? SN2. And that's how they got that group on the sulfur. Yeah? Pretty straightforward chemistry. So that's really a Friedel-Crafts alkylation. And what they do next, though? 17 to 18, what are they doing here? Now, this is just the same as this. We used FeBr3, aluminum, Br3, or okay. There are others you can use, and what other is tin? Okay? But the tin tetrachloride is a Lewis acid, just like aluminum trichloride. Okay? It's a Lewis acid. What's going on here? That's a Friedel-Crafts acylation. And what type of director is the sulfur here still? Orthopara. Where did the acyl group go? Para. Could they have also gotten some ortho? Theoretically, yes. They don't show what type of yield they got here. I don't know how much. Very often, para is more preferred than ortho. We talked about that. Particularly for Friedel-Crafts. Friedel-Crafts tend to kind of give a little bit more para than ortho. But again, theoretically, we predict both ortho and para. Now from there, this next reaction is pretty convoluted, and we may learn part of this as we get to carbonyl chemistry, but they convert that to an alkyne, and then they keep building the molecule. One thing you will see down here is the last reaction is a palladium catalyzed reaction that I mentioned in the 8-week lab pre-lecture. In 2010, palladium chemistry won Nobel Prize. That's an example of the palladium chemistry down there. This reaction, you know. You remember terminal alkynes? The H of a terminal alkyne has some acidity. N-butyllithium. It's deprotonating that and making this anion. And then that anion is reacting with the zinc and kicking off one of these chlorines, and that's how we get this carbon-zinc bond. So there's some examples of Friedel-Crafts there. Another example is in the synthesis of the drug Vioxx. Vioxx was a $1 million selling drug, $1 billion, 15 years ago. For treatment of arthritis. But it turned out it led to heart effects. And it had to be pulled from the market. And a lot of money was lost, okay? A lot of people crying about that in the drug industry. This shows the synthesis of that compound. And what's the very first reaction? Friedel-Crafts acylation, again with a sulfur there, para, okay. The sulfur's then oxidized. We won't see that, but that's a common reaction to make the sulfone. The next reaction is one we'll see during test 4, and that's halogenation at the alpha carbon of a carbonyl. Okay, we'll see that during test 4. Next, they come in here with this anion, and this anion here attacks the carbon and kicks off the bromine. And that's how they make that bond right there. So go to SN2, right? And from there, that molecule, they then do what's called an aldol condensation. And we will cover the aldol condensation during test 4 as well. Actually, during test 4, I will give you this handout again. Okay? But it does begin with a Friedel-Crafts acylation. So all this chemistry is really chemistry we're going to be covering. Except for the sulfur oxidation, but that's pretty straightforward. That's a common reaction of sulfur. Sulfur can actually oxidize and add oxygens to the sulfur. Okay, so some chemistry to look forward to. Any questions about Friedel-Crafts reactions? I'll just let you Okay, we'll have a quiz on Monday. It'll be over everything we've covered thus far for test 2. That includes aromaticity and EAS reactions, including substituent effects, which includes activation, deactivation, and directing effects. Okay? We have various EAS reactions, halogenation, nitration, sulfonation, et cetera, and now Friedel-Crafts alkylation and acylation. Thank you. So quiz on Monday. Okay, the next handout is yellow, and we'll look at substitution of leaving groups on aromatic rings. Traditional leaving groups, like halogen. Okay? This will be our other two mechanisms. This will be either NAS, nucleophilic aromatic substitution. And I mentioned our 3 mechanisms on the very first handout. EAS was the first one. These are our other 2. NAS and the benzyne mechanism. So in this example here, you see that the chlorine is being substituted by the nucleophile. Okay? So a more traditional leaving group. In an EAS, what is being replaced by the new group? What atom is being replaced by a new group?
Hydrogen.
It's actually a hydrogen. And you could actually say, hey, the hydrogen is gone. We can call it a leaving group. It's not really a leaving group because it doesn't leave as an anion. It doesn't take a lone pair with it. Okay? So it's not really like a leaving group like with SN1, SN2. Or here. Here, the leaving group is going to take a lone pair with it. And H does not do that in an EAS. Okay? And H, of course, is not a leaving group for SN1, SN2. But halogen is, and halogen here is more of a traditional leaving group that we can substitute, and we see that here. Only product form, no isomer. That will be important. Down here, if we try to do it, same conditions, same temperature, no reaction. Why? Well, apparently it has to do with this other group over. That's the difference. We need to understand what's going on. Down below, if you do this reaction at much higher temperature, 300 degrees, that's going to be a little hot. You don't want to touch that. Okay. All right. You can replace the traditional leaving group with the nucleophile. But somehow you get the nucleophile bonding to the other carbon as well. It ends up bonded here. What's going on here? Okay, so those are some warm-up questions to think about. Okay, substitution of leaving group by nucleophile. I have a leaving group, nucleophile. The nucleophile can replace the leaving group. Okay, we'll see how to do that. Since that's the nucleophile, the ring here is the what? The ring is the electrophile here. But the ring is reacting to the nucleophile. And so it's called, well, we got to be careful. There's two ways to do this. One way is nucleophilic aromatic substitution. Let's look at it. What's the mechanism? First off, is it SN2? Does a nucleophile just come in here and kick that off? No, why not? Because that's an sp2 carbon. And you never do SN1 or SN2 with an sp2 carbon, right? Remember that? It's not SN2. Also, backside attack is impossible. If you have to kind of see that. Also, if we did attack that carbon, what's the weakest bond? The bond to the leaving group or the pi bond group? Pi bond, right? We talked about that when we did reactions with like dinochloride and when we made tosylates, attack the sulfur, which, okay. I've rewatched the first week videos. Okay? It's not SN1 because that carbocation is very unstable and typically never formed. Okay? It's not EAS because the ring is reacting with a nucleophile, not an electrophile. Okay? The mechanism is either NAS or benzyne. Okay, looks like we're about out of time here. Well, got a couple of minutes. Let's see what I can do here. We'll basically pick up here. We'll do mechanism here, but then I'm going to tell you something, okay? For those of you who are going to look at this, you may see a problem with this as presented. That's because I'm going to present it, then we're going to go back and talk about the problem. Okay? And what's needed here to solve the problem. All right? Any last questions before we leave today? Okay. See some of you in lab this afternoon upstairs. Quiz on Monday. Have a good day, guys.